Welcome back. This is 11.2. We'll be looking at the second derivatives. That is, we will find the first derivative and then we're going to derive that again with respect to x. Now, why do we use this? We try to find the concavity of the graph. So if the first derivative is increasing, then your graph is concave upward. If the first derivative is decreasing, then your graph is concave downward. We've seen that if the first derivative is increasing, or if it's going upward, then your graph opens upward. If the first derivative is going downward, then the graph kind of opens downward. And concavity here, the summary is, so if the second derivative is greater than 0, that means your first derivative is increasing, of course, and the graph is concave upward. If the second derivative is less than 0, which is negative, that means the graph is decreasing and it's concave downward. I would like to put it this way. So I have the function. Let me just erase this one. Let me move right here and expand it. And I like to write it this way. So I have the function, I have the first derivative, and I have the second derivative. The second derivative is positive. That means the graph is increasing and it's concave upward. If the second derivative is negative, that means your first derivative is decreasing and your graph is concave downward. Okay? All right, now we've seen that. Let's take a look at the next term, which is inflection points. So if you have a function that is continuous and on the interval AB, then it has an inflection point at x is equal to c when the second derivative is equal to 0 and the second derivative does not exist. So what we're going to do here is we're going to use these theorems and we're going to go ahead and strategize the graph. What does that mean? So step 1, we analyze the function. That is, we find the domain and the intercepts. Step 2, we analyze the first derivative and we find the partition of the numbers and the critical values to determine the local maximum or the minimum. Step 3, we find the second derivative, find the partition, and determine the concavity. So here we'll find the inflection points, here we find the local maximum, local minimum, and you find the domain and intercept, and then we're going to graph all of that together. And I know you're thinking, Miss, why do we have to do all of that when we have our TI-84s or graphing calculators? You'll see why. So let's go ahead and take a look at the first problem here. It says find the second derivative. So what I'm going to do is I'm going to expand this one. I'm going to start with the first derivative of these two. And how does that work? It is negative 6 times 4, x to the power negative 6 minus 1. Negative 4 times negative 8, x to the power negative 8 minus 1. So when I combine these, what do I end up with? This is negative 6 times 4 is negative 24, x to the power negative 7. Negative 4 times negative 8 is positive 32, x to the power negative 9. And once I have this, I'm going to go ahead and find the derivative of this one now, which is going to be my second derivative. So f double prime of x is negative 7 times negative 24 times x to the power negative 7 minus 1. And here I have positive 32 times negative 9, x to the power negative 9 minus 1. And now if I combine these two, what do I end up with? 168, x to the power negative 8. Combine these two, I end up with 288, x to the power negative 10. So you're just finding the derivative twice so you can get the second derivative. All right, let's take a look at the next one here. Find the x and y coordinates of all inflection points. To find the inflection points, I have to find the derivative twice. So first step, first derivative, which is 3x squared. 18 times 2 is 36x. Now, it's inflection, so I have to find the second derivative, which is 3 times 2 is 6x plus 36. How do I find the inflection points? I set the second derivative equal to 0. So I have 6x is equal to negative 36. X is equal to negative 6. And once I have this, I will go ahead and plug my negative 6 into my function. And to do that, I'm going to use the space here. It is negative 6 whole cube plus 18 times negative 6 squared, which gives me 432. So my inflection points are negative 6, comma 432. All right. Now let's go ahead and take a look at the next problem here. Now you might say, Miss, why can't I just graph this and find my values? Try graphing it. Because of the nature of the function, finding those partition points becomes slightly difficult. So let's go ahead and see what they're asking us. Find the intervals on which the graph is concave upward. Find the intervals on which the graph is concave downward. And then the inflection points. All right, so let's go ahead and start. When they talk about inflection, concave upward, concave downward, you know that you're finding the first and the second derivative of the function. So not only the first one, you will also be finding the second derivative. So let's go ahead and take a look. Just give me 1 second. Let me have my calculator opened up here. In 1 minute, I should be ready. All right, so let's go ahead and copy down what the function is first. It says the function f of x is equal to ln x squared minus 4x plus 40. So because this is a log function, let me change my ln here. Because this is a log function, it's going to be slightly tedious. I want you all to pay attention here. So if you have your pen and paper ready, let's go ahead and work this out. First step, they're asking us, the term concave upward is used to describe how the graph opens upward, right? And downward is how the graph opens downward. So to find the concavity, so technically what I'm saying is I have f double prime of x, I have f prime of x, and I have the function x. Remember this table that we did in the beginning? So if this is positive, this is increasing, this is concave upward. If this is negative, this is decreasing, and this is concave downward. I'm going to go ahead, cut this one and move this, decrease this one and move this all the way here so we can have this available for us at all times. So to do that, first I have to find the first derivative. So f prime, this is ln x, the derivative of ln x is 1 over x times the derivative of x squared, which is, remember it's 1 over x times the derivative of this one, which is 2x minus 4. So if I simplify this, I have 2x minus 4 over x squared minus 4x plus 40. Now I'm finding the second derivative. Let me move this one also here. Now I'm finding the second derivative. The moment I see a fraction, remember the formula? It is x squared minus 4x plus 40 whole squared times x squared minus 4x plus 40 times the derivative of 2x minus 4, which is 2x, minus the derivative of x squared minus 40, which is 2x minus 4 times the first function, which is 2x minus 4. So quickly recap, how do you find the derivative of fractions? So you can go ahead and follow along with me. All right, so once that's done, let's go ahead and see what we can do. Let me multiply this one. I'm distributing this throughout. This is going to be slightly tedious. This is, oh, derivative of 2x minus 4 is 2. My bad, it's 2, not 2x. Okay, so this is 2x squared minus 8x plus 80 minus, I'm going to have a big parenthesis here because I'm multiplying these two, and I would get 4x squared. 8 times 2 is 16, negative 16x plus 16, the whole thing over x squared minus 4x plus 40 whole squared. Now you can graph this in your graphing calculator, but trust me, you will not find those inflection points. So I have to make sure I work this out. This is 2x squared minus 8x plus 80 minus 4x squared, plus, very careful, plus and minus 16. The whole thing over x squared minus 4x plus 40 whole squared. And now what is this equal to? Positive, negative, I have negative 2x squared. And this is going to be positive 8x, positive 8x. 80 minus 16 is positive 64. And the whole thing over x squared minus 4x plus 40 whole squared. Phew. Now that we have the second derivative, what do we do now? They're asking us to find the inflection points. Remember, the whole idea is to go ahead and tell me where the graph is concave upward or concave downward. Of course, you can graph this in your graphing calculator to cross-check to see if you're on the right track or no. But I'm trying to find the inflection points here. So to find the inflection points, what do? I will go ahead and set this whole thing, second derivative, to 0. Let's quickly go back here. Let me show you the formula. Let me erase this one. The inflection point is at x is equal to c when f double prime is equal to 0, or if it does not exist. So I'm going to go ahead, set that equal to 0. And now you might say, Miss, why am I not looking at when it does not exist? So when you look at if it does not exist, as you can see that this whole thing, where is that? X squared minus 4x plus 40. This whole thing whole squared is always greater than 0. So the denominator can never be 0 in this case. So this, let me expand. I'm talking about, this is a rational function, right? The denominator can never be equal to 0 because no matter what I plug in, I will always have this 40 squared. So there's no way this is going to be, the denominator is not equal to 0. That means there is no way, let me rephrase. That means my function is continuous. Let me just put it that way. My function is continuous. So what I'm going to do is to find inflection points. I'm going to make another column here. And I'm going to say to find the inflection points, I'm going to set my second derivative equal to 0, which is negative 2x squared plus 8x plus 64 over x squared minus 4x plus 40 whole squared. When I set this whole thing equal to 0, when I cross multiply, I am only left with 2x squared plus 8x plus 64 equal to 0. I'm going to divide everything with negative 2. I'm going to factor negative 2 out. When I factor negative 2, I'm going to get x squared minus 4x minus 32 equal to 0. And when I factor this further, factors are negative 8 and positive 4 equal to 0. That means my x is equal to positive 8 and x is equal to negative 4, which are my inflection points. Let's see if you're on the right track. Yeah, my inflection points are -4 and +8. Now you might say, Miss, what happens now? This is exactly what happens. When you have your inflection points, what you will do is these inflection points, I'm going to draw a number line. So x is equal to 8 is right here, and x is equal to -4 is right here. Remember, this is positive infinity, this is negative infinity. These inflection points will create those partitions, and now I can see what happens to my graph here, what happens to my graph here, and what happens to my graph from here to here. That means my interval is -infinity to -4, and -4 to +8, and 8 to infinity. What do? I simply take a couple of values and plug them in. So what I'm going to do, just to make sure, again, the goal here is to see if my function is either positive or negative, and I'm only trying to see where my function is going to be concave upward or concave downward. So all I have to do is I'm going to take a value from in between -4 and +4. I'm going to take a value 0. I'm going to use another number here, color. In here I'm going to take a number 9. In here I'm going to take -9. Just keep it simple. Now what do? Take these and plug them into the second derivative. So I'm going to take x is equal to 0 and plug into -2x squared plus 8x plus 64 whole thing divided by x squared minus 4x plus 40 whole square. And again, my goal is to see if this is going to be positive or negative, or what is going to be the value. So when I plug in 0 here, again, you can use your calculator to plug it in. You know what? Let me go ahead and show that to you. This is my Desmos calculator. So this is -2x squared. I think I totally forgot what it is. -2x squared plus 8x plus 64 divided by, I have, what was that? That was x squared minus 4x plus 40 whole squared. And all I'm going to do is I'm going to look at the table here. So when I plug in 0, let me expand this. No, I can't. When I plug in 0, I'm just looking if it's a positive or negative. I get a positive. When I plug +9, I get a negative. When I plug when I plug -9, I still get a negative. So technically, I'm not looking for the numbers. I'm just looking at this is positive, this is negative, and this is negative. Again, your second derivative is negative. So let's go back to our table here. Your second derivative is negative. Oops. Your second derivative is negative. That means your function is decreasing. It's concave downward. If it's positive, function is increasing, concave upward. So your second derivative is negative. That means the function is decreasing. This is concave downward. This is concave upward. And this is concave downward. And again, they're asking us, where is it concave upward? From -4 to +8. That's exactly what we have. Concave downward is from -infinity to -4 and 8 to infinity. -infinity to -4 and 8 to infinity. That's all, just by looking at it. But you can also graph this one. Let me show that to you as well. You can graph the function, which is ln parentheses, it is x squared minus 4x plus 40. See, it is, but it's very hard for you to find those inflection points which are -8, like this point, -8, and I think it was -8 and +4. No, -4 and +8. Yeah, -4 and +8. See, for you, it's hard to find those values, but as you can see, it is concave downward. And from this point, it's concave upward and then concave downward. You can go ahead and solve this however you want, but it's always important to know that you have to find the second derivative, set it equal to 0, find the inflection points, and then plug it back into the function just to see if it is positive or negative, so you can determine if the function is concave upward or downward. Again, you'll have to practice it multiple times so you can get used to it. All right, let's take a look at the next problem. Oh, this one, they're asking us to graph. Oops. They're asking us to graph this one. Let's see what all I have. The function is continuous. Very good. I have the value f of -6, f of 0, f of +6. Okay. F prime of 0 is 0. F prime of -6 and +6 are not defined. Okay. F prime is greater than 0 from 0 to 6, 6 to infinity. Okay. F prime is less than 0 from -6, -infinity to -6, 6 to 0, and this is what I have. Okay, so what I'm going to do is I'm going to go ahead and make sure I have like a block here. You know what I'm going to do? I'm going to erase this one, and here my points are. Trying to see what's the best way to do it. Let me take a screenshot of this one too. And let me go ahead and crop this one to see if I can crop it. I just want this part so I can use this and have everything with us. I don't want to copy it. I'm just being lazy. Okay. I want to cover that. Very good. That's the goal. All right. So what I'm going to do is I'm going to go ahead and draw the line here, right? What do we have? We have, again, they're giving us the points, which is -6, +6, right? F prime of 0 is 0, and I do have the values -6 and +6. So just by looking at those values, I know those are my partition values, -6 and +6. Okay, very good. I also have the function value. So if I graph this function, I have -6 is 0. Very good. +6 is 0, and f of 0 is -12. So this is a 0, this is a 0, -12. Very good. The graph has to join these two because, right? That's how it's going to be. And again, let's see what's happening next. F of -6 and the double prime, the second derivative of f of -6 and f of +6 are not defined. That's okay. And here, f double prime is greater than 0 from -6 to +6. Remember, if f double prime is greater than 0, that means it's positive. That means f prime is, f of x is increasing and it's concave upward. It's concave upward. So if we have f prime is less than 0, that means this is concave downward, this is concave upward. So the first part is taken care of us. It is concave upward. Now let's go ahead and see what happens in this area. What is happening in this area? This is going to be concave downward. That means your graph has to be something like this, right? Concave downward. But let's go ahead and see if that can help. It says this is less than 0. So this whole part is less than 0. Concave downward. This whole part is less than 0. Do not forget to put your infinities so it makes more sense. It says f double prime is less than 0 in this area. So that means it's going to be concave downward. So all I have to do is concave downward, concave downward. And let's see if it satisfies this one. F prime of x is greater than 0 from negative infinity to negative 6. Of course, that is going to be negative infinity to negative 6. As you can see, if f double prime is greater than 0, that means that is also greater than 0, right? And here also is the same thing. So once we've seen that, let's move this and see which one matches. And clearly this, this graph is a graph. Very simple. I simply join negative 6, 12, and positive 6 because these are the values given to me. And this part is going to be concave upward. If the second derivative is less than 0, that means it's going to be concave downward. This is going to be concave downward. And I'm also looking to see where my function satisfies the first derivative. F prime is less than 0. Negative infinity to negative 6 and 6 to 0. What does that mean? If f prime is less than 0, that means the function is decreasing. Look, the function is decreasing from negative 6 to negative infinity to negative 6 and negative 6 to 0. And starting from 0 to 6, the function is again increasing and increasing. So it does satisfy all the conditions. Hope this helps.